largest rectangle in histogram. Given an array of integer height representing the histogram bar height where the width of each bar is 1, return the area of the largest rectangle in the histogram. Okay, so let's try to understand the problem. We are given a histogram where each bar has a width of 1 and a certain height. Our task is to find the largest rectangular area that can be formed using consecutive bar. So we are taking this example. Okay, the most obvious way to think about this problem is to pick each bar one by one and assume that bar as the height of the rectangle. Okay, something like this. Fix a bar, we try to extend the bar. Once we fix a bar, we try to extend the rectangle to the left and to the right, as long as the bar at least has talls as the current bar. For example, if we pick a height 6 at index 2, we check left. On the left, bar 1 is smaller, so we stop. Similarly, on the right, bar 5 is smaller, so we stop again. So this rectangle has width 1 and area 6. We repeat this same process for every bar. So let's try to repeat this process for 5. For 5, 1, and on the right we got 3. So the width here is 3 and the height is 5, so area is 15. So this will work, but the problem is time complexity. For each of the n bars, in the worst case we can scan almost the entire array again. So the total time complexity will be n square. So here is the most important observation. When we pick a bar of some height, its rectangle ends exactly when we encounter a small bar. For example, for 5, a rectangle ends when we encounter 3, which is smaller than 5. So for every bar, the rectangle is bounded by the first smaller bar on the left and the first smaller bar on the right. Once both boundaries are known to us, the area is fixed. So if we ask here, the real question is, can we find the boundary efficiently without scanning again and again? Okay, so we did this kind of question previously as well. So maximum greater element. So in order to solve this efficiently, we have observed that we have to remember the length of each bar until we have encountered the smaller bar. Okay, and when it comes to remember, we will use a stack. So here stack will store indices, not height, because we want to calculate width. The stack will maintain bar height in increasing order, because as soon as we got the smaller one, we will stop. Our rectangle is fixed. At index 0, height is 2. At index 0, height is 2. The stack is empty, so we push index 0. Okay, at index 1, height is 1. This is smaller than the height at the top of the stack, which is 2. That means the rectangle with height 2 must end here. So we will pop out the index 0. We will calculate its area. So its area will be width into height of bar. So as we can see, stack is empty, so width will be the current index, which is 1, and height is 2. So area will become 2. Now we push index 1 into the stack. At index 2, height is 6. This is greater than the height at the top of the stack, which is 1, so we push index 2. At index 3, height is 5. This is smaller than 6. This is smaller than 6, so the rectangle with height 6 must end here. We need to pop out index 2. So for index 3, we have popped out height 6. Height 6. Width will be I minus top of a stack, which is 1 minus 1. So I is 3, that means 1. Area will be 6. Okay, area become now height 5 is greater than the height at stack top 1. So we push index 3. At index 4, height is 6, which is greater than 5. So we will put 4 as well. At index 5, height is 3. This is smaller than 6, so we pop index 4. Okay, so at I equal to 4, we will pop height will be 6 and width will be I, which is 5. Okay, I will be 5 minus top of stack, which is 4 minus 1 into 6. Area will be 6. Then height 3 is still less than height 5, so we will keep popping. Now for I equal to 5 only, height will be 6, 5. So now for I equal to 5, height will be 5, width will be I minus top of index, top of stack, which is 1, and minus 1. So area will be 5 into 3, that is 15. Okay, now height 3 is still smaller. Now height 3 is greater than height at the stack or top, which is 1, so we push index 5. We have reached the end of the histogram, but the stack is not empty. This means the remaining bars can extend still the end of the array. So after I equal to end, where we ended, So we will pop out 5, so height will be 3, index top will be 1, so width will be 6 minus 1 minus 1, area will be 12. And similarly for I equal to end, height equal to 1, width will be I, which is 6, as we are end of the stack, it will be 6. So for 1 it will be 6, for 3 it will be for 12, for 5, so 15 is the answer here. The reason this algorithm works efficiently is simple. Each index is pushed onto the stack 1, each index is popped from the stack once, so the total time complexity is n only. So the key idea is here, don't calculate early, wait until a smaller bar forces the rectangle to end. So that's all. In the last video we understood the theory of largest rectangle in histogram. Now in this video we will be trying to code it. So let's first create a stack. We will start from left. If you remember, we did this dry run. Starting from left to right, we will be storing indices, not height. The stack will always maintain bar in the increasing height order. As soon as we get a bar with a smaller height than the height of the top of the stack, we will resolve all the bars in the stack. So let's do it. While st.empty is false and st.top heights st.top is greater than xi. So if we get a bar which is less than the height of the bar on the top of the stack, we will start resolving. Int equal to temp st.pop with equal to if the stack is empty, then the width will be current I only, else I minus st.top. If we see this position of index 5, index I equal to 3, height will be 6, width is I minus 1 minus 1. That is I is the current element minus top of stack, I minus top of stack minus 1. Okay, so result is equals to into result max of result comma width into heights temp lst dot push I. Okay, once it is completed, we need to do it again to resolve all the remaining element in the stack. I equal to heights dot size done set. Okay, done.